Hello. In this video, I'm going to be solving two exercises from section 6.1 of Jiří Lebel's Notes on Diffy Qs. So this section's about Laplace transforms. It introduces them. And the two exercises I'm doing are related to Laplace transforms. So the first of our exercises, 6.1.5, is to find the Laplace transform of this function right here. And then the other exercise, 6.1.11, wants us to find the inverse now Laplace transform of this function right here. Okay, so let's first do this exercise. So, okay, first thing we need to remember is a key property of the Laplace transform. And that property is linearity. So this says that if I take the Laplace transform of two functions added together and scaled by constants a and b, then as long as f and g both have Laplace transforms, then I can find the Laplace transform of this linear combination of them by just factoring out the constants and adding the results, L of g of t. Okay. And so this is useful for us because now we can go to our example and we can compute that the Laplace transform of 3 plus t to the fifth plus sine of pi t. Well, we just need to do the Laplace transform of each part separately. 3 plus transform of t to the fifth plus the transform of sine of pi t. And once we find these three, we can add them up and get a result. Okay, but what are these Laplace transforms? We could always compute these by hand using the definition of the Laplace transform. So just recall that if f of t has a Laplace transform, it's given by, or we define it to be, rather, e to the minus st f of t dt. So it's this integral right here. And the domain is just wherever this integral converges. With domain, the set of S, where this integral converges. And that would be fine to do here. It would just be a little tedious and time consuming because it would involve usually a lot of integration by parts, especially with this example right here. And so, lucky for us, the smart minds of previous centuries have already tabulated some of these standard Laplace transforms. And so we can skip a lot of this calculation we would otherwise do by hand by just consulting tables like these. And so, okay, we just need to look at the functions we have up here and see where they match up on the corresponding table. So let's first look at this transform. We're taking the Laplace transform of a constant 3. Going down here, we see that there is an entry when f of t is a constant c, and the transform is given by c over s. So what we find is that the Laplace transform of 3, well, it's just going to be 3 over s. Now let's do the next term. We're taking the transform of t to the fifth, and if we go to our table, we have an entry for t, t squared, t cubed, and in general, the entry for t to the n, which is given by n factorial over s to the n plus 1. So, plugging in n equals 5, we get that this transform is 5 factorial divided by s to the 5 plus 1, which is 120 all over s to the 6th. And then finally, we have the final transform of sine of pi t. And this, okay, going to our table, we do have an entry for sine of omega t. Here omega is understood to be a constant. And the transform of sine of omega t is omega over s squared plus omega squared. So this transform works out to be pi over s squared plus pi squared. Therefore, from our previous work, the transform of 3 plus t to the 5th plus sine of pi t is just going to be the sum of these three functions right here. So it'll be 3 over s plus 120 over s to the 6th plus pi over s squared plus pi squared. Cool. All right. So now let's find the inverse transform of this function given to us here. So as a brief reminder, for the inverse transform, we go backwards. And what I mean by this is, like, say we know that the Laplace transform of f of t is some function, f of s. Then the inverse transform of f of s is just whatever function we plugged into the Laplace transform, namely f of t. So when computing inverse Laplace transforms, for example, using a table, we're instead going to look at the right side now and see like which of the terms match up with the things we're working with. And then we're going to go backwards and just like go back to the functions that generated that Laplace transform. Okay. But the problem here is that this function right here, as written, doesn't seem to match any of the entries on our table. I mean, over here, we have s minus 1 squared times s plus 1. And in all the cases of our table, there is no denominator that addresses the case where we have a product of distinct linear factors like that. So what do? Well, in general, whenever you have a rational function like this, you should always split it up using partial fraction decomposition. Okay. So first step, if the Laplace transform is a rational function, as I just mentioned, you should do partial fraction decomposition. The reason for doing this is because once we do this, we're going to express this function right here as a linear combination of simpler reciprocal functions that we know the inverse Laplace transforms to. Okay. Now I'll spare you all the boredom and detail of actually computing the partial fraction decomposition for this expression. But if you do it, it works out to be 1/4 over s plus 1 plus negative 1/4 over s minus 1 plus 1/2 over s minus 1 squared. And so, let me center this to make it look nice. This means that the inverse transform of 1 over s minus 1 squared, s plus 1, just as the normal Laplace transform is linear, so we can like just take, if we're adding up functions, we just take the Laplace transforms of the summands individually. The same thing holds for the inverse transform. So, well, this will be the inverse transform of this expression here, which I'm just going to duplicate. Come on. But by linearity of the inverse transform, well, we could just factor out any constants and then do the summands separately. So it's going to be 1/4 inverse transform of 1 over s plus 1 minus 1/4 inverse transform of 1 over s minus 1 plus 1/2 inverse transform of 1 over s minus 1 squared. Okay. Now the first two terms are easy. These actually correspond to entries in our table. Why is that the case? Well, let's start with the first term. It's 1 over s plus 1. And if we go to the table, we notice that it matches the form 1 over s plus a. Here in our case, a is equal to 1. So by just plugging in a equals 1, we find that this inverse transform is e to the minus t. Or if you want to be super careful, you could write it as e to the 1 minus t, negative 1 minus t. And similarly, over here we're doing 1 over s minus 1, which might not look like something that's on our table because we only have plus here. But we can make it look that way by just doing 1 over s plus negative 1 instead. And so now a is negative 1 in our transform, so the inverse Laplace transform is going to be, e to the negative, and now a is negative 1, so this is negative 1 times t. But now what about this term? This one is s minus 1 squared, and we don't have anything here that looks like s minus 1 squared. I mean, we have some s squareds right here, but here the constants are on the outside of the square. Here we have the constant on the inside. What do? Well, this one looks pretty similar to this transform right here, 1 over s squared. The only difference is that the input s is instead replaced with s minus 1. And this is where another key property of the inverse or the Laplace transform is going to be useful for us. Which is called the first, and I'm going to quote our notes, first shifting property. So suppose we know that the Laplace transform of a function, little f of t, is capital F of s. Then if I take the Laplace transform and I add some constant a, this has the effect of shifting the graph of capital F, hence the name first shifting property. This is the same as the Laplace transform of our function f of t, but now multiplied by e to the minus at, where a is whatever thing we added into the input at capital F, i.e. the thing that we're shifting capital F by. Now this is cool, but how is this useful to us? Because here we have a Laplace transform, but we're computing an inverse transform. Well, here we just need to take inverses. Therefore, this is saying that the inverse transform of f of s plus a is nothing more than f of t times e to the minus at. And the way we can make use of this is by noticing that 1 over s minus 1 squared, we can write this as 1 over, or we can write this, as f of s minus 1, where f of s is 1 over s squared. And this is good for us because we know what the inverse transform of 1 over s squared is. It's just t. So now to apply this shifting property, let's rewrite this in a way that looks like s plus a on the inside. But that's easy enough. We just need to do the same trick I did in blue up here. Instead of writing s minus 1, I'm going to write f of s plus negative 1. So then applying the shifting property, the inverse Laplace transform of 1 over s minus 1 squared, is going to be the inverse transform of f of s plus negative 1, where f is this function right here. And this will be equal to f of t times e to the negative 1 times t. where our f of t now, well, we just have to go to the table. The f of t corresponding to capital F here is t, little t. So this is t times e to the t, where now I've just canceled out the negatives. Thus, we conclude up here that this last term is 1/2 times t e to the t. And then we can clean this up by just making this exponential here, just making it e to the t. And this is, oops, almost the final answer. Let me make that cleaner too. This right here would be our final answer for the inverse Laplace transform. So once again, to summarize this shifting property, if you add something to the transform of a function, little f in this case, it corresponds to multiplying that function by e to the negative of a times t, where a is the thing you're adding. So right here, if we have our transform, we add a, and taking the inverse transform of capital F of s plus a, it gives us the inverse transform of capital F, namely little f, but now we multiply by e to the minus at, where again, a is just this constant here. All right, that wraps up this video. If there are any questions, please feel free to leave a comment. Otherwise, I will see you all in the next video.